Hi, this is a continuation of Chapter 1 of the Real Analysis series. In this video, we are going to learn about cardinality of a set. Here's a quick outline of the video. We'll first talk about meaning of cardinality of a set. We then move to the mathematical definition of finite sets. We then talk about countable and uncountable sets. We then look at the Cantor's theorem, which gives an example of an uncountable set. Alright, starting with the main question, what is the cardinality of a set? Given any set A, its cardinality is denoted like this. It is a measure of the number of elements, in the set A. To give you some examples, consider set A containing these elements 3, 5, 0, minus 8. Now the cardinality of this set is 4 because it has 4 elements. Similarly, if we consider another set containing 3, 9, 12, 19 and pi, there are 5 elements in this set. So the cardinality of this set is 5. Now for finite sets, it's easy to see what the cardinality is just by counting the number of elements in the set. But what about infinite sets? How do you count the number of elements in an infinite set? Well, for that, we are going to need a mathematical definition. So here's the definition. We start off with the definition of finite sets. Definition: we say that the cardinality of the set 1, 2 up to n, the set of n natural numbers, is n, and a set X is said to have cardinality n if there exists a bijection or a bijective function f from the set 1 up to n to set X. Now, what is the meaning of bijective function? A function f being bijective means that it has to satisfy the following two properties. The first property is, if you take distinct inputs I not equal to j, then the output is also distinct, fi is not equal to fj. This property is also called as injective property or 1-1 property of the function. And the second property is that for every x in X, X should be of the form f of I for some I in the domain of the function, here 1 up to n. This property is called surjection or surjective property of the function or ontoness. In diagrams, it can be represented this way. Suppose you have left side these elements 1 up to n, and right side you have elements say x1, x2 up to xn, and the function maps 1 to the first element, 2 to the second, and so on, and to the nth element. So this is the meaning of bijection. Now we have defined finite sets. Let us move to the definition of infinite sets. Now infinite sets are measured with respect to the set of natural numbers. Just as we measure finite sets with the set of finitely many natural numbers 1 up to n, we measure infinite sets with the set of natural numbers. And we say that the cardinality of natural numbers is the first cardinal number, and every other set is measured with respect to this cardinality. So here's the definition. Definition: a set, an infinite set, is said to be, an infinite set A is said to be denumerable if the cardinality of that set is the first cardinal number, which means that there exists a bijective map or bijective function f from the set of natural numbers to the set A in question. Now this word denumerable, it means that the set A is countable as well as infinite, which is also called countably infinite. Now this definition, what it tells is that an infinite set is denumerable if you can count its elements, meaning A is denumerable if there is a procedure. There is a procedure to list its elements as A1, A2, A3, and so on. Very nice. Moving on. An infinite set that is not denumerable is called uncountable. It's called uncountable. Very well, let's look at some examples. Here is the first example of a denumerable set. The set of integers is denumerable because we can enlist its elements as follows: 0, 1, -1, 2, -2, 3, -3, and so on. Here is another example of a denumerable set. The Cartesian product of the natural numbers is also denumerable. For that, let us enlist the elements of this Cartesian product. The first element is 1, 1, the second 1, 2, 1, 3, and 1, 4, like this. And then you also have 2, 1, 2, 2, 2, 3, 2, 4, and so on, going on like this. Now, it is easy to specify a procedure to count each of these elements like this. You follow these lines and you will be able to count each and every element of this set. Very nice. The last part of this chapter is going to be an example of uncountable set, which is given by the Cantor's theorem. Cantor's theorem, it states that the power set of natural numbers, which is denoted as 2 superscript the set of natural numbers, this is the power set, meaning the set of all subsets of natural numbers, is uncountable. Here's a quick proof of this. We know that the power set of natural numbers contains all the singleton sets of natural numbers. That is why this power set 2 power n is an infinite set. Now let us assume, for the sake of contradiction, that this set is not uncountable. Not uncountable. Then what does it mean? If it is not uncountable, we know that it is infinite. So this means that the set is denumerable. Because this set is denumerable, so there exists a bijective function call that function phi from the set of natural numbers to this power set. This is a bijective function. Now here's the trick. You consider this subset of natural numbers. The set D consists of the natural numbers n such that n does not belong to phi of n. Now this is a subset of natural numbers, so this belongs to the power set of n. Now since this phi is bijection, in particular onto, so there exists some m natural number such that this set D is of the form phi of m. Now here's the contradiction. From this equality we know that m belongs to phi of m if and only if m belongs to D, but we know by the definition of D that m belongs to D if and only if m does not belong to phi of m. So we started with m belongs to phi, we got m does not belong to phi of m, and vice versa. So these two statements contradict each other. So we arrive at a contradiction. Now, why did we get the contradiction in the first place? It is because our assumption that 2 power n is not uncountable is wrong, and hence the Cantor's theorem is proved. And the cardinality of this set is known as the second cardinal number. You take the power set of natural numbers, you get third cardinal number, and so on.